All right, hello, my name is Wade Hines, and I'm at Brown University. I'm going to speak briefly about my paper, Galois uniformity and quadratic dynamics over K of t. So in order to do that, let me fix some notation. So for our purposes, K will be a field of characteristic 0, and phi will be a polynomial with coefficients in K of degree d. So a lot of the stuff that I'm going to talk about goes through for rational functions d, but it's just easier to focus on the polynomial case, and so that's what we'll do. So phi to the n in this talk will be the nth iterative phi, or phi composed with itself n times. And the basic object we're going to act on is Tn of phi, which is just the set of roots of all iterates of phi. So the roots of phi 0, phi 1, up to phi n. And this, if we adjoin these roots to K, then we obtain a field extension, which I'll denote K sub n. All right. And so the remark is, well, it's this T sub n phi is not just a set. It actually has a nice tree structure. It's a d-area rooted tree structure under some mild assumptions called the preimage tree. And the basic idea is that we define two elements in T sub n phi to share an edge if and only if phi evaluates one to the other. Okay, so if that didn't make sense, then let's just look at an example. So let k be the rational numbers and phi of x just be the quadratic polynomial x squared plus 1. Then t2 of phi, well, we adjoin 0, the root of the 0th iterate, and then the roots I and negative I of the first iterative phi. And then the second iterative phi is going to be a degree 4 polynomial, so we'll have 4 roots. But those roots come in pairs, namely if they evaluate to either I or negative I under evaluation of phi. Okay, so now let's build up the Galois machinery. So let's let Gn of phi be the Galois group of Kn over K, and G infinity of phi be the inverse limit of these set of groups. And finally, T infinity phi will just be the set of adjoining all roots of all iterates of phi. And the point being is that since our polynomial we started with has coefficients over K, that Galois commutes with evaluation. So we get injective homomorphisms from Gn of phi into the automorphism group of a tree, here and here. And these are called the arboreal representations. And so a basic question to ask is, well, what type of subgroup do these images give us here? And that's what my paper does. So the big theorem that I prove is that if K is Kt, so K, little k here, is a characteristic 0 field, and D equals 2, so I have a polynomial, a quadratic polynomial with coefficients over little kt, then I not only get a finite index subgroup, so G infinity phi gives me a finite index subgroup of aught T infinity phi, but I get a uniform bound on that index outside of an explicit set of phis. So this is where that term uniformity in the title comes from. We get a uniform bound on the index. And just a remark that this is similar to Serre's uniformity conjecture for elliptic curves over a number field. Basically, if you replace our polynomial phi with a multiplication by L map and replace T infinity of phi with an L-adic Tate module, then Serre conjectured a similar result for the Galois representation of elliptic curves, that the bound on the index shouldn't depend on the elliptic curve. And so that's where this fits in. So if you have any questions about this paper or just Galois representations and arithmetic dynamics in general, feel free to email me. If not, thanks for your time.